Okay, this is the next video in PySpark, and here we're going to deal with window functions. So as SQL supports window functions, so does Spark support window functions. Here are examples of windows that are being provided. This is called window partition by stock code order by invoice date. This is partition by stock code or order by quantity descending, or partition by stock code order by unit price descending. You can use partition clause, order by clause. There is also rows between clause, which we are going to cover later. Okay, first exercise, assign sequential row number per product. So I specified window directly, and I will be specifying them directly in the majority of cases below. So we simply take row number. Here we PySpark import functions as f, and here we imported window. So f row number over and replace window inside over partition by stock code order by voice code. So we have run row number in the stock code partition with the ordering by invoice date. Our task is to create sequential number. So as we can see, same stock code, invoice date, and this is row number, but the amount of stock codes is too much. This is the second function, which is count over partition by stock code, simple window without any order, and there are 33 stock codes, so the row numbers go beyond the horizon. Here, however, I filtered those stock codes which have not so many sales, from 4 to 6, and that's what we see. 4 stock codes, 4 is against each row, and the rows are numbered. Here we have 5 stock codes, and along the increasing date they are numbered, and so do the rest. 5 stock codes, and they are numbered in the increasing date. So where the dates collide, I believe we don't have the situation here. The number will increase. Again, rank rows by quantity with gaps for ties. So rank with gaps for ties means we have simple rank. We don't have dense rank, which avoids these gaps. So it works same as row number, same partition by first field, order by second field. So we are ranked by quantity. So quantity, as you can see within one stock code, quantity is 13444, rank is 12333. These are ties. 3 is a tie. Here another example. We have quantity 120, 120, 120, 120, 480. So these are ones. Then we have a gap, and then goes 5. This is, so we have 4 values as ties on position number 1. Okay, another example, 1 which was ranked as 12225, and this was ranked as 11145 because the values increase. Okay, now we get dense rank. Dense rank is different from the rank in that the ranking is condensed. There are no gaps. Okay, on the first example we have the same result, 1, 2, 3, 3. It's not the same, but on the second example We have 1, 1, 1, 1, and then 2. Here we have 1, 1, 1, 1, and then 5. Okay, on this one, 1, 2, 2, 2, and then 5. Here we are going to have 3. Yes. Here we have 1, 1, 2, 3. So this is called dense rank because it doesn't have gaps. Percent rank of quantity per product. So percent rank works basically the same way as rank, but the ranking is in terms of percent. So the whole scale is considered to be 1, and let us say we have 10 places, so they are placed from 0, 1 to 0, 9, and 1. Let's see how it works. So we have certain scale, and the percent rank goes along that scale. You see, this is simple rank 1, 2, 2, 4, but in terms of percent, it went 0, 0.333, 0.333, and then 1. Let's see how it works here. Ranking 1, 2, 3, 3, and this is percentile rank 0, 0, 25, 5, 5, 5, 5. Now, this is another example, 1, 1, 1, 4. So first placement is 0 and the next is 1. Here we have a spread of values and it goes 0, 0, 663, 0, 666. We didn't reach 1. In this case, the first values were on 0 and the last value is on 1. Here we have again the scale of percentiles. Here the values, actually, here is an example that the values are spread 0, 0.4, 0.6, 0.81. This has ties, 0, 25, 25, and so on. So the percentile rank is not dense, it has gaps, as we can see here. Okay, cumulative distribution of quantity per product. So we simply use function cumulative distribution of stock code ordered by products. Let's see what we've got. So this is certain stock code. This is quantity, and as we go, we accumulate increasing value. So, and this is called cumulative distribution. Here, the same, 0.3, 0.3, and we go on. Here, we start with 0.4, and so on. Here, we start with 3 small values, and with the values are bigger, and we reach 1. This is how cumulative distribution works. Divide rows into 4 buckets by invoice date. Okay, we need to take all the amount of rows and divide them into 4 buckets, 4 groups. This is done by NTILE. NTILE requires partition. Partition is by nothing here, so we just partition the whole row. But we bucketed it by invoice date, and here are the amount of buckets we obtained. So the whole number of rows was divided into 4 parts of almost the same size. Certain buckets might be one element larger than others. Okay. Here is another example. I have now created buckets with partition by stock code, and what we see here is this. So 4 elements for the stock code, and each one of them went into a separate. No, they didn't. This is the amount of elements in the bucket. So this one got 6 in each bucket. This one got 2 8s and 2 7s. This one got 1 element per bucket, and so on. So bucket basically distributes elements into equal or almost equal groups. Compute total sales quantity per stock code. So basically we are summarizing quantity by stock code, and this is not quite a window function with this is the simple aggregate. Okay, compute average unit price per stock code. This is the same as above but average. Count distinct months per product. This is again simple aggregation of count distinct. Exercise 10. Compute cumulative sum of quantity over time per product. So the quantity should increase within the partition of stock code and ordered by invoice date. So here is what we've got. We have various invoice lines, and they got different quantities: 4, 3, 4, 1, 6. And as we go, cumulative quantity increases. This is first plus second. This is first plus second plus third. With this adds 1, this adds 4. Here again, so it increases as we go. We go in the direction of increasing date within the partition of certain stock code. The increase goes within partition, within stock code, and it increases along the date. So as you can see, within each stock code, the cumulative value does increase. It works even for negative numbers. Here, negative numbers, which returns or something. Yes, and as you can see, I believe it's not. No, it's sorted by order by. It increases as we go. But I believe the beginning is missing here. So it's minus 14, minus 12, minus 10, you know, it adds numbers. Okay, compute moving average of unit price over last 2 rows per product. Here we got rows between. This rows between statement is the key one here. So we've got aggregate function, we've got window, which is partitioned by stock code, ordered by invoice date, but we take only rows between -2 and current row. Let's see what we've got. We take a single stock code, and we have average. Okay, here in the stock code it doesn't much matter. This is also not a good example, but we can see in the last one it calculated average of the last 3, so it's not .12 but .8. This one, as you can see, the last 2 values are less, so average has decreased a bit. So yes, it decreased because of this value. Okay, this one, you know, the price goes down, the average goes down along the price, but it's sort of delays because it's average over the last 3. Okay, here also we have decrease in average, but it doesn't come to 0 because it's average over the last 3 elements. Again, here we see the average first goes down, then goes up because of this decrease and then increase. This is called moving average. It moves along the line. Lead of quantity to see next order's quantity. Okay, within the partition of stock code and ordering by invoice date, we see the next value. And the next value is the value of quantity. So what do we see? We see quantity 4, and this and next quantity is 3. Is 3 the quantity from the next line. Here again 4, 4, 1, 1, and the last quantity goes into nothing and is null. Okay, so again here we see the 1 row delay. So this is called lead, so we look forward. Log of quantity to see previous orders. This is the function log. It works the same way but in a backward direction. It runs so this is the group, the partition, and you see this is quantity 4 and this is the previous quantity 1, and now we have it in the beginning. I have added one more test, and here I used the second parameter of log. The second parameter of log can tell how many rows we can go back. As you can see, delay now is not 1 row but actually 2 rows. You see this 1, 3 and 3 is 2 rows back, and in the beginning we have 2 nulls because 2 first rows cannot first rows do not have previous elements if we go 2 rows back. Here is another parameter, third parameter. We can replace null with some other value. Here I replaced it with zeros. Okay, let's calculate the difference between current and the previous value, and it's simply done. We calculate log, we take current value and we subtract it from previous value. What we should watch for is that difference between non-null and null would produce null. So 4 minus null equals null. To avoid this situation I have created here, this example, we have to use NTILE function. So I reduced null values to 0. So even though we have 4 and null, the result is 4. So we have non-null difference, but we should use NTILE, or we can use coalesce. Which is equivalent to NTILE. Okay, rank by unit price per product. So we are ranking price, and we are ranking it within the partition by stock code and ordering by unit price. This is what we've done so far, and there is nothing to read. So this is unit price is the same, we always got 1. Unit price is not the same, we got 1, 2, 2, 2, 2. Here this is rank, so we might have gaps somewhere. Do we have? Yes, we have gaps here. You see 1, 1, then 3, 3, and then 5. This is a simple rank, and it has gaps. And also it has gaps here, and we have gaps here. Okay, I assigned dense rank by unit price per product. This is the same thing. just different partition by and order by, and under the same circumstances, here we've got 1, 1, 2, 2, 3. See, we have dense rank 1, 2, 3 on 5 elements. We don't have gaps. Here we have here we have 1, 2, 3, 4, 4. This one, okay. Okay, no more good examples here. Just dense rank doesn't have gaps. Exercise 17, cumulative distribution of unit price. Okay, we've got this 0 to 1 estimate of how values are distributed. And you can see, depending on the, okay, here the values have significant increase, so they distribute in the certain percent. So basically 0.2 is 1/5 of so this 125 is about 20% of 762. That's what the meaning. Okay, another example on this. Okay, first is 40%, then 80%, and then this is 1. This is how it's distributed. Calculate row number partitioned by stock code and customer ID. So here we have double partitioned by 2 fields and 1 order. So there could be any amount of fields in partitioned by and any amount of fields in order by. In partition by we can have 0 fields, in order by we should have at least 1 field. So this is a window, this is row number by this window, and here is how we've got it. So this one is 1, 2, 3. Do we have repeated? Yes, we have repeated stock code and different customers here, so the ranking goes within each customer for the same stock code, which goes 15 lines in a row. NTILE of quantity into 3 buckets per stock code. So this is NTILE, which we have seen above. We partitioned by it by stock code and ordered by quantity. So okay, this is certain stock code. We have brought it into how many? Yes, you see, 2 rows into bucket 1, 2 rows into bucket 2, and 2 rows into bucket 3. That's how it goes. So basically we place them into buckets. Okay, combine multiple ranking functions into one frame. So these are multiple functions. Row num rank, we can see dense rank against normal rank. Okay, you see row number and rank are different because the order by is different. This is ordered by different fields. So one is ordered by date, and another one is ordered by quantity. So the rank was ordered by quantity, and 6 is against the highest quantity. Dense rank doesn't increase. Percent rank quantity, this is percent, cumulative distribution, and NTILE of buckets. We have spread them into certain buckets. You see, buckets have been done within a certain partition. This is the last example repeated, but the functions are isolated into a separate dictionary, and basically this the query is calculated on the fly. So we have went over this dictionary, we have added columns dynamically, column name, column column definition. This is a more compact way in case you need to calculate something very extensive, and but the result is the same as in the previous one. Okay, I will skip some of the examples because they repeat what we have already done. This is window minimum. So we run minimum over window stock date. Window stock date was defined above, yes. Partition by stock date, ordered by invoice date. So minimum is run from current point backward. See what we've got here. As we go on in the increase of invoice date, we get minimum over previous rows. This is because the window was ordered. You see, because of this order by invoice date, we get minimum but in the increasing order. This basically means rows between unbounded preceding and current row. Okay, same for maximum, but here we get the maximum to the back. So you see, as soon as we reached this 180, the maximum is 180. 1, 2, 2, here we still have 2. So as we go on, the maximum catches backwards. Compute cumulative counts of rows per stock code. So we are counting rows, and rows do increase, but this is actually tantamount to row number. As we go forward, we count rows, and this becomes a row number. Get first quantity per stock code in the window. Basically nothing to read. We get the first quantity as we go back. We had minimum in the above, but here we have first, which is not necessarily minimum. You see what we've got. This is the same, this is the same. Yes, we got 3, which is the first, but it is not minimum. Okay, get last quantity per stock code in the window. The last means we have the same sorting window stock date, but we have to specify a window between current row and unbounded following, and we got last 4 is this 4. 120 is this 120. Here we have minus 23, which is the last value. Here we got 10, which is the last value. And here we got minus 16, which is the last value. Compute moving of sum of last 3 quantity per stock code. This is moving average of last 3, but last 3 is minus 2 to 0, 3 elements including the current element. And we got sum over 3 last elements. So you see, here we got 9, and it's a sum of 4 plus 1 plus 4. Here we got 8, and it's a sum of 3 plus 4 plus 1. Here we got the sum of previous 3. Okay, here we got 13, which is the sum of the last 3 elements. Here we got 3, which is the sum of these 3 ones. Compute moving average of last 3 unit price per stock code. Basically the same thing, average of the last 3. In the ordering, okay, what we've, here we have interesting situation. This is the wrong result. We have to put quantity. Okay, it is now correct. We take 3 last quantities and we got average of them. So this is 9 divided by 3, we got 3. This was 8 divided by 3, and this was 11 divided by 3. Here we got only 2 elements, which is 4 and 3, and we divided them by 2, and here we got 4 divided by 1. Okay, what we've got here also, this 10 average, this is 2, so it's the current element and 2 elements back. Compute max price per stock quote up to current row. So max unit price over this window, rows between unbounded preceding and current row. So here it was not important, and here in these rows we get the maximum value from the beginning. Here on the last example, we see that maximum is increases as we go. At the first row we have only 0, and the second we have 3.75, and here we've got 7.62, which stays, because if we go backwards the maximum is 7.62. Compute min unit price per stock quote up to current row. This is the same thing, but minimum, rows between unbounded preceding and current row. And here we can see that minimum is calculated based on the previous rows. When the value increases, it doesn't increase the minimum. Count number of invoices per stock quote up to current row. We are counting number up to the current row. This is not distinct count, this is normal count in the ordering. So basically it's tantamount to row number. So we are counting invoices. If we had some of the stock quote null, we would skip numbers. It won't count nulls. Get first unit price per stock quote. First over window, this is the same, but first function we have already done it. Get last unit price per stock quote. This is the last value or within a certain partition. Yes, as you can see, the last value is 24.95b. BOA, you have to specify between current row and unbounded following, otherwise it won't go ahead of you. Compute cumulative sum of quantity per stock quote and customer ID. This is accumulation of the sum running total, which is partitioned by 2 values, stock quote and customer ID, and within each it increases. Compute cumulative average of unit price per stock quote. This is the same, but for average 2 partitioned functions. This is not very important. Here the average changes as we go. Compute cumulative max of quantity per stock quote and customer ID. This is maximum in window stock customer. This is maximum by 2 fields, nothing really significant. Compute cumulative minimum. This is the same thing for minimum. Not going to concentrate on that. Count cumulative number of rows per stock quote and customer ID, partitioned by 2 fields. Actually, here it also partitioned by 2 fields, and we count in cumulative. Same as row numbers, unless we hit nulls. Get first and last unit price per stock quote and customer ID. Here we got first and last value at the same time. which in some cases are, yes, you see, this is first is 0.85 and the last is 0.42. And pay attention to use between current row and unbounded following. Here unbounded preceding and current row is optional. It can it goes by default with order by. Okay, so we have completed it.